So I want to start the discussion about the continuous random state as well also measurements with giving you a kind of a use case over here. So we meet our kind of another structure, another radar structure. Remember that this structure we also saw in the binary kind of classification problem. So we have, if you like, a radar tower with a kind of a flat panel array over here, antenna, that it is sort of whose job is really to estimate the location of a drone. Let me just represent the drone with this kind of symbol over here. And, out of the, obviously we live in a kind of a three-dimensional, in reality, coordinate system where we have, let's say, the x-axis over here, the z-axis coming out of this kind of page, and the y-axis. We are going to just limit the discussion here in one dimension. And evidently, at any point in time, the location of the drone is, of course, given by some kinematic equations. Let me write the first one. Let's say x0 plus some vx, the projection of the velocity component in the x-axis, times delta t. And I'll explain what delta t is, plus 1 over 2 ax delta t squared. Okay, so the delta t is the time that it takes for the antenna array to rotate 360 degrees. So the radars have this kind of rotating antennas, either electronically rotated or mechanically kind of rotated in the older kind of versions of them. But they are sort of trying to get a 360 degree coverage around them to detect incoming, let's say, drones. And this is basically the delta t. Every delta t, we will actually be getting a measurement. And let's assume now that we also write down the y and the z. I'm not going to write these kind of equations. Ax is the acceleration, and the acceleration component at the x-axis. So it's a kind of a very simple kinematic kind of model that defines, where the location of the drone will be given some velocities and some accelerations, okay, some initial location. All right, so so the question that actually we are posing over here is the following. What is the optimal way to estimate xt, and this is at every moment in time we have an xt location, okay, when we receive sequentially measurements I will call these measurements ZT. That is the question. Okay, so all right. So if we am to assume some kind of the measurements which are effectively going to be given by an additive model, where the measurement is going to be definitely depend on the location of the drone, the true location of the drone xt, plus some epsilon, some error that governs, if you like, the random variable which indicates the measurement. So this is effectively my measurement model. And my epsilon is going to be normal, let's say with zero mean and some kind of variance. That is my error. Okay, and I think if you kind of represent what is going to happen in terms of a kind of estimator that we want to develop. So we, over time, so we may be starting, although the true location of the drone is around xt, we may be starting at every sort of square over here represents delta t. So this is delta t over here, this is 2 delta t, and so on. This is in general t times delta t. Maybe starting from some initial kind of estimate of that kind of location, and gradually, as the measurements are actually coming in, we will be converging into some around the true value. That is what's supposed to be happening in this kind of estimation approach. All right, so we will also be assuming, for the purposes of avoiding to involve the kinematic kind of model, that right now the drone is modeling, is hovering. And there's no wind, and so the xt is at this is going to be constant. So we are going to be looking at this kind of stationary kind of model to make the discussion a bit simpler. And also we make the assumption, let me also write the other assumption, is that every delta t we get a measurement. Okay. Now, if you remember that video in a kind of previous video when we were looking at the maximum likelihood estimation about Gaussian random variables, and I hope you recognize that this ZT is a Gaussian random variable because we are adding a constant as per the assumption over here into a Gaussian kind of error signal. We actually have wrote down the maximum likelihood estimate of the Gaussian random variables, and we had two estimates of the Gaussian parameter. So we have a probability distribution that governs now ZT, and this probability distribution has two parameters, the mean and the variance. And so right now I'm actually interested to write down the equation about the maximum likelihood estimate. The best, according to that maximum likelihood criterion, estimate of xt is 1 over t, the number of samples that we have received at this moment in time, t. So this goes from, let's say, I is equal to 1 to t, and then we have zi. So the location, effectively, that we are interested in to find is really the mean of this Gaussian probability distribution, because you're adding a zero mean component into a constant. That constant goes and takes the place of the mean of the z of this variable z. So, and this is this is from this formula over here is from maximum likelihood estimate of the mean of a Gaussian random variable. Okay, so, and for those who kind of forgotten the derivation over there, it's I think they can review the so-called marginal maximum likelihood video to recall that kind of formula. So, all right, so we have this formula. Okay, we have now the estimate. So let me rewrite this as 1 over t. I'll break down the summation into two parts. The summation from I is equal to 1 to t minus 1 and zi plus zt. So, and then now I'm going to write the 1 over t summation from I is equal to 1 to t minus 1 zi plus 1 over t zt. And I'm going to write the first one as 1 over t. I'm going to multiply with t minus 1 and divide with t minus 1 the summation from I is equal to 1 to t minus 1 zi plus 1 over t zt. So it is t minus 1 over t. Now this whole thing over here is exactly the MLE when I have t minus 1 samples plus 1 over t zt. And therefore this becomes 1 minus 1 over t, that is this, xt minus 1 MLE. MLE, of course, stands for maximum likelihood estimate, plus 1 over t zt. And therefore, I'm actually going to write now the final form of this, which is xt MLE is equal to xt minus 1 MLE plus, I will write this capital KT. I will write this factor capital KT, and actually I'm going to write capital KT, yeah, this factor, and then I'm going to write it as ZT minus XT minus 1 MLE. Where capital T, capital KT, I will call it later the so-called Kalman gain. This obviously does not have something to do with recursive state estimation. It has something to do with recursive state estimation, but right now we are just looking at the maximum likelihood estimate that we can actually form from so-called streaming data. Streaming measurements are actually coming in one after another. So the formula kind of says something like this: the current estimate is the previous estimate plus a gain factor of the difference between the current measurement minus the previous estimate. This one is sometimes called in the literature innovation, or that indicates the new thing that we have learned from the measurement that came in, or residual. And this formula will actually be kind of instructive. Mind you that this KT is going to be a factor between 0 and 1. And this formula is actually going to give us the ability to update our estimate given, if you like, the current measurement that actually came in and the previous estimate. Notice also that in this kind of discussion we had this definition about the so-called gain in this kind of formula, but later will become the Kalman gain. And this is definitely a function of t. So initially the gain is 1, and then as the time goes by, the gain is reduces, and which means that initially the gain is putting quite a lot of emphasis in the in this kind of difference, and then this difference, the so-called information that comes out of measurements, in other words, is amplified initially and then kind of is tailing off. Some behavior like this we'll see explicitly in the Kalman filter equations that are to follow. So up to now, we have not really discussed anything about recursive state estimation. The only thing, as we have done it earlier, the Bayes filter, we have not talked about the Bayes filter at all, or anything Bayesian treatment at all, because we have not really mentioned anything about the prior. So what we will do next is we will introduce, if you like, this prior and start writing the one of the two equations, and I'm going to start with the second equation of the base filter. So we will assume, so let's assume that the prior over the location, let me call this P of xt, is given by a normal distribution of, let's say, we used the notation before, x0 given mu 0 and sigma 0 squared. So there is some prior that information we have about the location, if you like, of the drone. And if I start with the second, equation, the so-called measurement update, so measurement update, we will definitely can write it again, Bell, the belief for the location of the drone xt is eta times the probability of zt given xt times the belief hat of xt. Okay, and nothing changes with respect to what we have seen earlier in the discrete kind of case. And the only thing that we are going to be assuming over here is that the prior is Gaussian. So the belief hat of xt is Gaussian. And the probability, the measurement zt given xt is also Gaussian. And we saw how this kind of Gaussianity for the measurement kind of led to writing the maximum likelihood estimate as an expression over there, and then how that maximum likelihood estimate can be recursively kind of updated itself. Then the posterior, if these two are Gaussians, if both of these and these are Gaussian, then the posterior after the measurement update is also Gaussian. And so we'll see now that that's actually the kind of important result. We'll see now the curves, how they look in a kind of a notebook kind of setting, and just understand how the difference between the how far away, let's say, the prior information, which is the belief hat over there, and the measurement. So the belief hat is what was the state of affairs after that kinematic movement. So we have not really talked about kinematic movement because we started with the second kind of equation, but that was basically what was predicted to be our state after that kind of kinematic movement. And then that's Gaussian, and this will actually also be assumed to be Gaussian. So we will see now how the difference between the two Gaussian probability distribution affects the posterior. So we have some kind of visualization because it's not entirely obvious. And the second thing we need to come up with, and given the fact that this one is also Gaussian, then we need to write down the expression about the mean and the variance of that Gaussian distribution, which governs the posterior, the belief of our state. So as it turns out, this is analytically tractable because of the Gaussian de-assumption, and that's what we'll do next.